So we were talking about numbering systems, right? And then we were looked at the binary number system. We talked about, bases. We talked about um, whole numbers. We talked about integers. We talked about uh, looked at the decimal number system, radix, engineer notation. Talked about real numbers. Uh, our PLC calls them floating point numbers, by the way, and we'll look at that. But these are real numbers. So real numbers are made up of, they can be signed, plus or minus, and they can have a fractional component. So we deal with that. We probably won't deal with any any real numbers this semester. But when we get in, if you take ILT 196 and we start getting into the math and all that kind of stuff, you'll definitely, especially when you divide. So we have two types of integers. We have signed integers and we have unsigned integers, and we'll talk about that. And we'll need to understand a little bit about the binary number system to even understand that. So PLCs have basically four number systems that we deal with. The one we love is decimal. Oops, let me turn on the projector. So these are the four basic number systems used by PLC. Decimal, which we're going to be predominantly using this semester. Binary. We're going to look at binary a little bit because when we look at the inputs and outputs, it's going to be binary, right? And we're going to look. Octal is a base 8 number system, and hexadecimal is a base 8 number system. Computers deal primarily with decimal, binary, and hexadecimal. If you really, 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 really want to learn these computers, there's configuration files that the computer uses. We call it the registry. And this keeps all the information about every application and everything that goes on in the computer. If you can play around with, if you don't know what you're doing, so if you get in there in the registry, you mess something up, your computer might crash and not work anymore. That's how critical it is. So it's kind of like doing brain surgery. You want, when you have brain surgery, you want somebody that gets in there that really, really knows what they're doing, right? Because all it takes is one little slip of a knife, and you can't talk anymore or something like that. But the information that you enter in the registry is either going to be decimal, or it's going to be binary, or it's going to be hex. So computers stopped using the octal numbering system a long time ago. But originally we had 8-bit microprocessors. And octal is a base 8 system. So this is why octal was the very first high-level number system that we used, that the application or the computer used to display large binary numbers. So decimal we understand. Binary we kind of understand. Octal we probably don't understand that yet. And then hexadecimal is what we was working on when we left last class. So we know the advantage of binary. We know the advantage of octal. We know the advantage of hexadecimal. We got through this. And then we got into looking the binary number system. If we understand the least significant digit and most significant digit in the decimal number system, then we should understand least significant bit and most significant bit. Everybody okay so far? So we're just back reviewing. And so we called it a base 2 because it deals with exponents. All number systems deals with exponents. And we start off with the least significant bit because we don't have a fractional component here. We start off with the base raised to a power starting with what? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And I've given y'all those chart that shows you those powers, right? The first few are pretty good. You can do most of those in your head. But when we convert them to decimal, instead of actually using what it is, what we do is we just come up here and write the decimal equivalent of the power of 2, right? So we'd say 1, 2, 4, 8, 16, 32, 64, 128, and 256. And I'm not doing that, and I'm not doing multiplying by 2 in my head. It's just that I've dealt with the binary number system so long, I know these numbers. And then what do we do to convert it to decimal? So before it means anything to us, so to us, when we look at that binary number, it looks like it's a huge number because we're comparing it to the decimal numbering system, right? But it's not a huge number because each one of those digits, the decimal numbering system, each digit can hold 10 combinations. In the binary, each digit can only have what? It can only have 2. So the less number of combinations you have, the longer the number is going to be to represent the decimal equivalent. So what would we do here to get this to decimal, guys? No, we're trying to convert this binary number into a decimal number. What would we do? We add the decimal equivalent of the digits that have 1 in them. We ignore the 0. Because if I was to write this down in positional notation, it would be 1 times 2 to the 8th plus 0 times 2 to the 7th. Well, what's 0 times any number? So that means the zeros hold no weight to the number, right? You understand? So all we do to convert this to decimal, we write down our decimal equivalent across the top, and we add the bits. We add the decimal equivalent for the bits that have 1s in them. So I'd add 256. I'd add 32. I would add 16. I would add 8. And I would add 2. And whatever you come up with is the decimal weight of this binary number, which is what we need to do because we don't understand binary, right? You understand? We want to see this as a decimal number. What does that come up to be? Get your pencil out and do it. You're going to have to do this on a test and everything. You're going to have to do this on a lab we're going to do. So you might as well let me know you know how to do it now, right? What's that? 214? 314. Yeah, I should have known it was. It has to be greater than 256, right? 314. And that's decimal. So to make sure that these combinations of numbers is legal, or symbols, is legal in the octal number system, it's legal in the hexadecimal number system, and it's legal in the decimal number system. So what I'll try to make sure is I'm going to tell you, it'll either say convert this to decimal, or I'll put the little subscript down there so we know what base it is. So now that means something to me. So when I look at this big old binary number, I think it's a real big number, right? You understand? I think it's up in the millions. But it's not. It's only equal to 314. Because each combination, each digit only has 2 combinations. So the more combinations a numbering system has per digit, the smaller the numbers are going to be, right? You understand that? Develop a table. So that's all we'll do. We just develop a table, right? Just go start with 1. This is not 0. This is 2 to the 0. And any number raised to the 0 power is 1. So I knew this was going to be an even number. Why? Because that's the odd bit right there. So if this bit's a 1, then you're going to expect an odd answer. If the bit is a 0, you're going to expect an even answer. So just because we came up with an even answer didn't mean it's right. It just means it has a chance of being right, right? So if you've got so an even number in any number system is going to be an even number in any number system, right? Does that make sense? Okay, so let's do this. Let's say 535. Y'all convert that for me. Well, we'll come up and we'll make a chart, right? We'll start off with what? 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, which should be enough. 512, Rich. But I usually like to go one pass to make sure I have enough digits. It would be 1,024. Okay, then what do? Yeah, subtract the biggest one I can, right? Okay. Okay, so y'all sound like y'all can do it, so go ahead. That's a 12, by the way, 512. And then write a 1 every time you can subtract, right? And write a 0 if you can't subtract. So I know this is an odd number. So you, first of all, you're going to run out of, you're going to subtract a 0 somewhere down this line. You better be, by the time you get to this guy right here, if you still got something to subtract, it means you did it wrong, right? You understand that? If this subtracts to be 0, then you fill in the rest of it with zeros. What we start with right here? Okay. Oops, sorry. There we go. 1. What? 0. Everybody got that? Anybody need to see it work? So in if I wanted to give you this number in hexadecimal, what would I do? We already talked about that too. What I'd do is I'd come over here on the least significant bit, which is right here, and I would split this into groups of 4s. 1, 2, 3, 4. 1, 2, 3, 4. And then I pretend I can add zeros to the left-hand side as long as I want to. It has no weight. It doesn't change the weight of the number, right? Then I would look on that chart and I would write down what the, of course, this should be easy. So this would be a what? A 2, 1, 7. But this is base 16. Now, the problem we have right now is that 217, we want to see that as 217, but it's not. So technically, you shouldn't say that. You should say 217, base 16. Of course, you'll find out people that's been dealing with this for so long, they'll say 217, base 16, which is not technically correct. So we can take, so which one would be easier for me to give to you? 1 0 0 0 0 0 1 0 1 1 1. Even I had to wait, right, for y'all, or 217. 217. You could get that in your head, and then you'd just come up here and to convert it to binary, you'd just use groups of 4. So I'd come down and I'd do a 2, then I'd come down and I'd do a 1, and then I'd come down and I'd do a 7, and that's base 2. So after you deal with hex a lot, you literally visualize the binary number. So this is the way we would go. So this is why we use hexadecimal. We don't use hexadecimal. We use hexadecimal, or the application uses hexadecimal to display large binary numbers. So, you know, if you came up here and so this is system information, and we're going to come up here and look at hardware, and we'll just look at memory. So this is the actual memory layout of this computer, and these are addresses. Think about that binary number. That's 1, 2, 3, 4, 5, 6, 7, 8, right? Think about me writing that binary number out. So what the application is doing is it's displaying it in hexadecimal, right? So what is it? F2 5 3 3 F F F. Okay. So I could come over here now, and if I wanted to see the binary number, I understand it's hexadecimal, but if I wanted to see the binary number, F2 5 3 3 3 3 F F F, then that F2 5 3 3 F F F. That's 3 of. So think about the computer trying to display this address for you in binary. First of all, if I come up here and I let this if I said y'all copy this number down, what would you do? You'd be doing this, and then all of a sudden the ones and zeros start running together. So it would be even hard for you to copy a binary number this long. It would be hard for you to copy it down and not make what? Not make mistakes. So this is why we use this high-level number system. Even though this computer is a binary device, it runs programs, and programs are turning on a bunch of dots on a screen, right? You understand? And it can display anything. It can take this, so it's got a memory in there, and when it sees this pattern, it displays the pattern for an F, right? You understand that? When it sees 111, so it's no problem. It's a problem for the people that wrote the application that does it. It's very, very impressive, but it makes it really easy on us when they display these big binary numbers in what? Using hexadecimal. It's called system information. You can look at all the addresses inside your computer. So everything in your computer, if the microprocessor's got to communicate with it, everything in your computer's got an address, right? And if you did machine language programming, you would have to know all those addresses. You would have to know those because you're controlling everything. Luckily, our computer controls it for us. The application or your operating system controls the memory for you. So when you load in an application, you don't have to decide where it's stored. The operating system decides what memory is allocated to it, right? So it's really neat. But it's got to give us that information. So that's where we was at. We was actually on hexadecimal. Hexadecimal is what we call a base 16, so it means each digit has 16 combinations, and that's why we can do it. So how do we calculate the number of combinations a number system has? We take the base, right? And raise it to the number of digits that we're dealing with. So if I've got 2 to the 5th, means I could represent, with 5 bits of binary, I could represent 32 combinations. Well, with 4 bits of binary, 2 to the 4th, we can represent 16. And then 1 digit of base 16, I can represent 16. So since these come out to be exactly the same, that means I can use 4 bits of binary to represent each hex digit. And that's why it works. Octal, we have to split up in 3s, but we'll look at that in a minute. And like I said, in these computers, they don't use the octal numbering system anymore, but PLCs does. So PLCs are in this thing to keep downward compatibility. So when people learn the octal numbering system, they don't have to learn hexadecimal. So the first high-level numbering system that we used in programmable controllers is octal. So that's why they still support it. Windows gave up on that a long time ago. They kept support for these 8-bit applications that was written when we first got the first IBM compatible computer. And then when we moved to 16-bit applications, they kept support for 8, and we moved to 32-bit applications. They kept support for 8, but when we moved to 64-bit applications, they dropped all that. So I've got some programs that I wrote that won't run under Windows 10 anymore because they finally gave up all that downward compatibility. So binary here, counting in binary. We did some math. Most of y'all didn't understand that, but we're not going to do math in this class. The book, I think the book teaches it. We understand these names, right? So these groups have names. So a group of 4 bits, we call that each binary digit, we call it a bit. A group of 4, we call it a nibble. A group of 8, we called it a byte. A group of 16, we called it a word. A group of 32 in PLCs, we called it a what? Long word. Now this is where RS Logic 500 gives up. So the biggest numbers that we can represent on RS Logic 500 is 32 bits. Quad word in PLCs, this is computers. In PLCs, they refer to it as a double long word, and this is a group of 64 bits. So some of your newer processors allow you to deal with double long words. If you take PLC 2, we're using a compact logic instead of a micro logic. It's a compact logic, and it gets up to 64 bits. But that's a big number, right? So 64 bits would be 2 to the 64th. That's how many combinations we could represent. I'm looking for this guy, so I can bring my calculator up. I'm going to switch it back to scientific. Now I'm looking for my y to the x right here. So 2 raised to the 64th. That's the number we could represent. I don't know of any industry out there that's using PLCs but need numbers bigger than that, right? Now, if we sign them, and we'll talk about this later, when we sign them, when we use signed, we only get half of those combinations. But still, that is a huge number. I wouldn't even know how to say that number. So 64 bits is fine as far as numbering systems goes. Signed, we only get half of the combinations. And unsigned, we get all the combinations. And we'll look at that a little bit, why that happens when we move through the course. Hexadecimal number system. Some people call it hex. We have digits 0 through 9. Then we go, what, A, B, C, D, E, F, right? So this is counting in hexadecimal, only up to 15. So if I was counting in hex, I would go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. What would come next? Yeah, A, B, C, D, E, F. What comes next? No, there's no G. So let's say I'm counting in 10. I'm base 10. We'll start with 0. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. I want to keep counting. What do? Yeah, we'd stick a 1 up here and we stick a 0 up there, right? You understand? So that's what happens when I get to F. I'd go this. But that's not 10. That's actually 16. So 1, 0, no matter what base you're in, 1, 0 equals to the base. Those symbols equals to the base. Then I'd go 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, 7, 1, 8, 1, 9, 1, A, 1, B, 1, C, 1, D, 1, E, 1, F. What comes next? 2, 0. 2, 0 is twice the base, right? So that's actually equal to 32. Then I would count 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6, 2, 7, 2, 8, 2, 9, 2, A, 2, B, 2, C, 2, D, 2, E, 2, F, 3, 0, right? So that's the way we count. So y'all don't understand this guy right here is what you do, what we don't. That equals to the base. So every time we run out of combinations, the next time we go to 1, 0, 2, 0, 3, 0, 4, 0, 5, 0, 6, 0, 7, 0, just like that, right? You understand? As soon as we go through the number of combinations, then we finally go to, A0, A1, A2, A0, B0, C0, E0, F0, and then we'd go to 1, 0, 0. It's kind of like getting to 100, right? You understand? But that is not equal to 100. And we want to say that. It's 1, 0, 0, base 16, right? So that's the way we count. And I know it's confusing, but if you understand numbers, if I'm counting in binary, I go 0, 1. I've run out of combinations. What do? 1, 0. That's the base. Then I'd go what? Then I'd go 1, 1, right? Right? And I've run out of combinations. So what do? I go, good, 1, 0, 0, right? So that's the way we count. So every time you run out of combinations, you stick a number 1 out there and fill in with zeros, right? So that was good. So yeah, that usually happens when we count. So a lot of people want to call this 10, but that's always equal to the base. So that's 16. That would be right there would be 32, right? Because we counted to it twice. If I converted them to decimal. So to form hex numbers from binary groups, we split them into groups of 4s, right? So we can take a big binary number. So hopefully y'all see that. To me, I didn't want to do that. So let's say we have this hexadecimal right here, 3BC5. This is base 16. Y'all convert that to binary for me. Right, 0, 0, 1, 1, 0, 1, 1, right? What's next? 0, 0, good. And that would be base 2. So those two numbers are equal to each other. They are exactly equal to each other. We're just looking at the same number in two different bases. Now, when I converted, if I was going to convert the number to decimal, we got two options. We could convert it to binary and then do powers of 2s, right? 1, 2, 4, 8, 16, 32. Or we could do it using what we call positional notation. So I'd say 3 times, so this would be 16 to the 0, 16 to the first, 16 to the second, 16 to the third. So I'd say 3 times 16 to the third. So what's 16 to the third? It's on y'all's chart there. What's that? No, that's times 16 to the third. Isn't it on your chart? Don't you have it? What's that? Yeah, 4,096. I can multiply that out. Then I could say B. Oh, let me. Sorry, I got ahead of myself. Let me find my eraser. That wasn't right. So here you would have to use a calculator. But this can be done. So it'd be 3 times 4,096 equals. Then I'd say B. What's B equal to in decimal? 11 times 16 squared. What's 16 squared? Huh? What's that? 256. Then I'd say 12 times 16. Then I would say 5 times 1. And then when I got all that, when I got all these digits over here, I'd add them together. Or this would take you a calculator, right? Or we could do it. You could do it longhand, right? 4 digits is not bad, but 5 digits you're dealing with 16 to the 4th, right? So the longer they are, the more complicated this right here would be. But it's so easy to go through what? Through binary. So you got two options. You can do it this way, or you can do it this way. 1, 2, 4, 8, 16, 32, 64, 128, 256. I need to spread my number out. 512, 1,024, 2,048, 8,192, 16,384. And you can just do what? You could add the bits that have ones in them. So it's up to you. This you'd probably have to have a calculator. This you could probably do in your head. Well, not true, but you could do it a lot easier, right? Does that make sense? So it's up to you. When you look at the worksheet that we'll try to work on today, you can take each one of those, convert the hex digit over to decimal, then multiply it times the power of 6, the actual decimal equivalent of the power of 16. power 16. And then this is the decimal equivalent for each digit. Now you say, okay, I'm just going to use the calculator that does that for me. I'm a firm believer that if you don't know how to do it without a calculator, you don't need to use a calculator. So yeah, I can do that. I mean, I get this Windows calculator right here. This will do. What can I do on this thing? I can put it in what? I can put it in programmer. I can come up here and select a what? Select a base. Hex. I can enter the hex number 3BC5. And this gives me the binary already, but here's decimal. Here's what it looked like in octal, and here's what it would look like in binary. But you need to learn how to do this without a calculator, because you might not always have a what? Calculator with you, even though most people have their cell phones now. You can download, I don't know if the Windows calculator, if you're running the newest version of Windows. Let's see, let me find my calculator. I know it's in here somewhere. Oh, there it is. You can. You can download a calculator to it. I just wonder if I don't see where this switches into a programmer's calculator. All it does is engineering and then just a standard calculator. But yeah, there's all kind of calculators you can download. So hexadecimal, what do we use? What does the PLC use hexadecimal for? What do we use it? It allows us to represent very large binary numbers with very few digits. And it's so much easier for the computer to display those numbers using base 16 than it is binary. It gets very, 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 very cumbersome after a while, right? The only problem we have is if I give you a number like this, you automatically see it as what? You see it as decimal. So that's why I make sure I subscript these numbers for you. That is not decimal. That is not equal to 370. It's equal to a lot bigger number because hex is a lot more efficient than decimal, because decimal, each digit only has 10 combinations. Hexadecimal, each digit has what? 16. So that means I can represent bigger numbers with fewer digits with hex too. So this is counting. Let's count in hexadecimal. We've already done that. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. A, B, C, D, E, F, 1, 0. 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, 7, 1, 8, 1, 9, 1, A, 1, B, 1, C, 1, D, 1, E, 1, F. 2, 0. 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6, 2, 7, 2, 8, 2, 9, 2, A. Our normal, we've been counting in base 10 all this time. When we hit 2, 9, right, we want to go what? We want to go to 30. I don't know what to do about that, guys. 2, 9, 2A, 2B, 2C, 2D, 2E, 2F, 3, 0. And this goes all the way up to FF, which is equal, look, FF is equal to 255 in decimal. So here I represent it with 2 digits. Here in base 10, it took 3. So we can represent larger decimal numbers with fewer digits, and we can definitely represent larger binary numbers with fewer digits. So that's something we have to get through with, right? And notice when we count, we usually start with 0. Usually when you count with 1. But in computers, 0 means something. Like I say, it's like the football player that's got 0 as the number. It doesn't mean they don't exist, right? Because it's representing an address or something like that. So we have address 0. The octal numbering system, this is still used by PLCs. Has a base of 8. Therefore, there are only 8 combinations, 0 through 7. This gets people confused. Used to display the memory maps, carry out math operator instructions, and some PLC controllers. So this guy supports octal, it supports hex, it supports decimal, and it supports binary. And the newest PLCs that we have supports those 4 numbering systems. So this is octal, 0 through 7. So if I was counting in octal, it would go 0, 1, 2, 3, 4, 5, 6, 7. I've run out of combinations. What do I need to do? Put 1, 0. That's exactly right. Good. And this really gets people confused. 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, 7, which would be 2, 0. It should actually be 16. We're counting, so that's why we count in octal. And this is the problem we have, is that we got 2 bases that has it. So, you know, if I come up here and say 375, that could be what? That could be base 10, which is what we see it as. That could be base 16, or it could be base 8. Those are all legal symbols for those 3 numbering systems. If I come over here and do this, I know it can't be octal because there's two illegal digits in there. But it can still be what? It can still be decimal, or it can still be hex. That's why we have to make sure we specify which base. So on your test, it'll say convert the following binary number into hexadecimal, or something like that on the test. So that's why when I do it on the board, I'll come up here and make sure I specify what base it is, right? Does that make sense? There's no such thing as an 8 in the octal number system. So I think that's on the test. Which one of these is an invalid octal number? From an octal number for a binary, what we do in octal is we do basically the same thing. So let's say I have let me pop in a blank page here. So let's say I have a decimal number. Let's say I have 463. Okay, this is base 10. Okay, so y'all convert that to binary for me. Well, we're going binary. We'll go hex in a minute. So the number, all your numbers will start off with a 1, right? So what we got? Okay, 1, 0, 0. Hex we don't even have to add the 0 out there if you can see it, right? And then what comes next? 0, 1, 0. Is this right? Okay. Yeah. So somebody we're going to decimal. We're not going to hex. This is base 10. So we can't go, and this is another people make mistakes. I'll put a decimal number up there, and they'll use groups of 4s. You can't go between the decimal number system and the binary number system by using groups of 4s. And that's a mistake that a lot of people make. They think they learned that method, and they think they can do it for any numbering system, but you can't. So what I'd have to do is and when I go to binary, what am I going to have to do? I'm going to have to set up my chart, right? 1, 2, 4, 8, 16, 32, 64, 128, 256, 512. Another thing we have is people will subtract this from that. That's another mistake we have. And you're going to go from this to that. So if I go from this, right, to that, then that means we're going to do it that way. So I know I got a 256. So what do we got? I'm listening. No, I'm going to binary. I was demonstrating. Y'all was supposed to do this to binary for me. What do we get for our binary number? I'm listening. Huh? What do we get for a binary number? Okay, no number. If I was going to come up here and add, you wouldn't write a decimal number. You wouldn't write, you was going to write 10, you wouldn't write 10 like that. So the first thing I'm going to put in my binary number is going to be a 1. I know I can subtract a 256 from it, right? You understand? So I know I'm going to have a 1 right there. I'm not going to put a 0 right there right now because we're going from decimal to binary. Okay, what comes next? 1. What would be in the 256, 128 bit? So what's going on, guys? What did y'all do? Y'all didn't use groups of 4s to go from base 10 to base 2, did you? You didn't say 0, 1, 0, 0. That's not the way this works, right? So I would come over here if I was going to do this. So let's do it in class. And this is a common mistake people do. Once they learn that groups of 4s, they want to do that on everything. They say, "Oh man, that's easy." What do you mean? No, let's take the number you're giving me and let's convert it to decimal. If I'm reading you right, I might be wrong. So you're saying it's equal to this: 100,011,0011. That's what you're telling me, right? Okay, so let's go 1. Let's convert it to decimal. 1248. Right where? Okay. Well, maybe I'm wrong. So y'all give me the binary number that y'all came up with. And we'll convert it over. We'll check it. Okay, so you're right. I'm listening. 1 1. No, this is base 10. This is base 10. We're going from base 10 to base 2. So let's take this number y'all coming up with. You're coming up with this number right here, 4, and then you're telling me it's this, right? And then you're telling me it's this. Well, if I go 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, I know it's not right because you're saying I have a 512 when there's no way in the world I can get 512 into that. Yeah, and that's the problem. It's not this up here, and that's a mistake people make. They learn you grab those digits and you use 4-digit combination. That only works going from base 16 to base 2. We're not going from base 16 to base 2. What base is this? 10. So we're going from base 10 to base 2. And this is a tendency, I'm saying this is a tendency everybody does, and you're going to screw up because you need to pay attention to the base. So the way we would do this is I would subtract the biggest power of 2, decimal equivalent of power of 2 that I can subtract from 463. So I'd say 463 minus 256. That's the biggest thing I can subtract. Then I would put a 1 right there. The only thing going to groups of 4s, the only thing that does is when you're going from hexadecimal to binary. We're not going from hexadecimal to binary. We're going from base 10 to binary, right? So anybody got it? I know 256 is going to be a 1. So what's 463 minus 256? What's that? 207. Can I get a 128? Okay, so I'd put a 1 right there, and I'd subtract 128. And what do we come up with? 79. Can I subtract the 64 from 79? I put a 1 right there, and I subtract the 64. What does that leave me? Can I subtract the 32 from 15? No. Can I subtract the 16, 15? No. Can I subtract an 8? Yes. What does that leave me? What's that? 7. Can I subtract? Well, I can do that. That's a 7. 423 is a 7. So that's the binary number. But this is the problem we have, is that once you learn hex, you think you can do it that way, right? Groups of 4s. But you can't. Now, if I wanted to go to hex, I would come up here and take my binary number, and I would split this into groups of 4s, starting with the least significant bit. 1, 2, 3, 4. 1, 2, 3, 1, 2, 3, 4. And this would be 1, C, F. So if I'd have wrote 1 CF up there, everybody would have got it right. But see, that's the problem we have, is that you see those numbers up there, and automatically you want to do it in groups of 4s. That only works from what? Going from hexadecimal over to binary. So is that right? So I'm going to use my calculator to double check that, because we did have some problems. Let's clear. There it is. So put it in hex. 1 CF. Oops. Clear, Rich. 1 CF. Okay, so that's hex. So in decimal, that would equal to 463. So that's right. So y'all got to watch out for that, right? Very common mistake. I realized something was going on when y'all did it so fast. Of course, it would have been faster with a calculator. Now, so I'm going to come up here and erase. So that's the same number in hex. This is the number in binary. All these are equal to each other.